Okay, so think about this for a second. Have you ever looked at something and thought, wow, that is like an exact copy?
Mm.
You know, like you're flipping through a fresh set of pictures from one of those old photo booths,
Yeah, yeah.
and every single one is just a perfect replica.
Okay.
Or maybe you've seen like a really neat stack of those delicate glass bangles,
Mm-hmm.
and each one just fits so perfectly on top of the next one.
Right.
Or even something as basic as like uh, grabbing a couple of coins that were all minted in the same year.
Interesting.
You know, if you were to take two 1 rupee coins and just lay one right on top of the other, there's like absolutely no difference.
Yeah, right.
They align perfectly.
Yeah, that feeling of flawless sameness.
Exactly.
That's precisely what we're going to unpack today.
I believe-
Beloved the
And
relative.
our focus for this deep dive is triangles. And you've probably encountered these before.
Oh, I'm sure.
Back in, geometry class in school.
Right.
And we're working with a source that actually has like a whole chapter just dedicated to them.
Dedicated to triangles.
So think of this deep dive as building upon what you probably already know
Okay. Yeah.
and really exploring this foundational idea,
Okay.
the concept of congruent triangles.
Okay.
And then we're going to look at some of their fascinating characteristics and properties.
Oh, good.
Our goal here, as always, is to really distill the most important insights from this material.
Of course.
Make it clear and engaging for you.
Right.
So,
Before we jump into, what makes these triangles congruent,
Yeah.
maybe we should just quickly refresh.
yeah, get on the same page.
What a triangle even is.
Exactly.
According to our source.
Right.
What's the definition here?
So a triangle, at its core, is a closed shape
Okay.
formed by 3 lines
Right.
that intersect each other.
Yeah.
So you get 3 sides,
Mm-hmm.
3 angles that are kind of tucked inside,
Yeah.
and 3 points where those lines meet.
Right.
And those are called the vertices.
Services. Okay.
So if you picture like a standard triangle in your mind,
Yeah.
we're going to label those points A, B, and C.
Okay.
So we can refer to it as triangle ABC.
Perfect.
So just a little shorthand.
Makes sense.
Now, when we talk about congruent figures,
Right.
what does that even mean?
Yeah. What does congruent actually mean?
In a broader
Answer
sense.
sense. Yeah.
So the text defines congruent as equal in all respects.
Okay.
So we're talking about figures where both the shape
Mm-hmm.
and their size
Okay.
are absolutely identical.
Okay.
So think about 2 circles.
Okay.
If they have the same radius,
Yeah.
they're congruent.
They're congruent.
Same applies to squares.
Okay.
If their sides has the same length,
Mm-hmm.
then those 2 squares are congruent.
Right.
What about equilateral triangles?
Yeah.
If all 3 sides of one
Right.
are the same as all 3 sides of another,
Then they're congruent.
then those are congruent.
But it's easy to think of congruence as just kind of this piece of abstract,
Just
geometry. But our source actually highlights some real-world examples of why this idea is important.
This is where it gets really cool.
It does.
So consider something like an ice cube tray,
yeah,
in your freezer.
an ice cube tray.
All those little compartments that form the ice,
Yeah,
they need to be congruent.
they do.
The mold that creates the tray,
Right.
it has all these identical depressions,
I see.
whether they're square or circular or even triangular.
Mm-hmm.
This need for exact sameness,
Yeah,
it's huge in manufacturing.
it is.
And it goes beyond just, big things like ice trays.
Yeah.
Have you ever tried to replace a pen refill?
Yeah.
And it just wasn't quite the right size.
Yeah. That's rough.
That's congruence in action,
That's
or really a lack thereof.
or like thereof. Yeah.
So if the new refill is congruent to the old one,
Mm-hmm.
it fits perfectly.
Right.
No fuss.
No problem.
It makes you think about all the times where we need things to be exactly the same.
Yeah.
And we don't even really think about it.
It's true.
Can you think of other times in your daily life where things absolutely need to be identical?
Think about electronics, like all those little components.
Oh, yeah.
They have to be exactly the right size and shape,
Absolutely.
or even standardized clothing sizes.
Mm-hmm.
So now let's bring this idea of congruence specifically to triangles.
Okay.
Under what conditions
Yeah.
can we definitively say that 2 triangles are congruent?
So according to the text,
Mm-hmm.
2 triangles are congruent when all 3 sides of one triangle
Okay.
are equal in length to the corresponding 3 sides of the other triangle,
Right.
and all 3 angles of one triangle
Mm-hmm.
are equal in measure to the corresponding 3 angles of the other triangle.
Yeah, and that idea of corresponding parts,
Yeah.
that's really important.
That's key.
So let's imagine we have 2 congruent triangles. We'll
Yeah.
call them triangle PQR and triangle ABC.
Got it.
If they're truly congruent,
Right.
then side PQ must have the same length as side AB.
Yeah.
Side QR must equal side BC. And side RP must have the same length as side CA.
It's like they're mirrored.
And similarly,
Okay.
angle P must have the same measure as angle A.
Yeah.
Angle Q must equal angle B.
Right.
And angle R must equal angle C.
Right.
It's all about those matching parts.
And the way we actually write this symbolically is also important.
Oh, absolutely.
So if triangle PQR is congruent to triangle ABC,
Okay.
we write it like this, triangle PQR, and then this little symbol that looks like an equal sign with a squiggle on top,
Right.
and then triangle ABC.
Okay.
And the order of the letters matters.
Yes, it does.
So P goes with A,
Right.
Q with B,
Right.
and R with C.
So if you were to write something like triangle QRP
Yeah,
is congruent to triangle ABC, that would be incorrect
that would be wrong.
because the letters don't match up in the right way.
The order matters.
The order matters.
And this actually leads to a really useful little abbreviation in geometry.
Oh, yeah, what's that?
CPCT. What is that? It stands for corresponding parts of congruent triangles are equal.
Okay.
So when you've proven that two triangles are congruent,
Mm-hmm.
using one of the rules that we're going to discuss,
Okay.
CPCT lets you say, hey,
Yeah.
all their other corresponding sides and angles
Mm-hmm.
are also equal.
So it's a shortcut
It's a huge shortcut.
for proving things.
It's kind of like saying, if we know these two puzzle pieces are exactly the same,
Right.
every single detail on one must match the other.
I like that analogy.
So now that we know what it means for triangles to be congruent,
Mm-hmm.
the next question is how much information do we actually need
That's a good point.
to know for sure?
Do we need to know all 6 corresponding parts?
Right.
All 3 sides and all 3 angles?
Do we need all that?
To be absolutely certain.
Because if we know that all 6 are the same,
Yeah.
they're definitely congruent.
Right. They would be.
But it turns out
Mm-hmm.
we don't always need all that.
Okay.
And the text starts by talking about some ideas
Yeah.
that sound good at first,
Okay.
but they don't actually work.
So it's like misconceptions almost.
Exactly.
Yeah.
So let's start with a simple one.
Okay.
If one side of a triangle
Uh-huh.
is the same length as one side of another triangle,
Yeah.
does that mean the triangles themselves are congruent?
Well, it seems logical.
It does, but the text shows why it's not enough.
Okay.
And they use a figure to help explain it.
Yeah.
It's called figure 7.5.
Okay.
And you can easily imagine two triangles
Right.
that look totally different,
Mm-hmm.
but they just happen to share one side.
Yeah.
That's the same length.
I see what you mean.
But all the other sides and angles
Could be completely different.
could be totally different.
Yeah.
So having just one matching side,
Yeah.
it's not enough to guarantee.
It doesn't lock it in.
So then what about this? What
Yeah.
if we know that one side and one angle
Okay.
of one triangle
Mm-hmm.
are the same as the corresponding side and angle of another triangle?
Okay, so a side and an angle are the same.
Exactly. And again, it seems like that might be enough,
It does.
but the text shows us why it's not.
How so?
They use figure 7.6 to illustrate this one.
Okay.
And you can see how that equal angle,
Right.
it could be positioned differently
Oh, I see.
relative to the equal side.
So the angle could be like
Yeah.
in a different spot.
Yeah, like flipped or rotated or
Yeah,
something.
yeah.
Or the other sides could have different lengths.
Right.
And then you end up with triangles that are clearly not congruent.
So one side and one angle matching up is not enough either.
Not quite enough.
Okay.
So this brings us to the first rule that actually works.
Right, I'm ready.
It's called SAS,
Pass.
which stands for side, angle, side.
Side, angle, side.
And in the text, this is given as an axiom,
Okay.
axiom 7.1.
Okay.
It says that two triangles are congruent
Mm-hmm.
if two sides of one triangle are equal in length
Okay.
to two sides of another triangle,
Two corresponding sides, right?
and the angle between those sides
Yeah.
in both triangles is also equal.
Okay, so the angle has to be included between the two sides.
Yes, exactly.
It can't just be any angle.
That word included is so important.
Right, like it's the hinge that kind
Yes.
of connects those two sides together
It locks it in.
and creates that unique triangle shape.
I like that.
So are there examples of this in the text?
Yes, there are.
Okay.
So example 1, it refers to figure 7.8,
Okay.
and we've got two line segments, OA and OB, that are equal in length,
Okay.
and then OD and OC, which are also equal,
Right.
and then the angles in between,
Mhm.
angle A and angle B,
Yeah.
those are vertically opposite angles,
Okay.
so they're equal.
Right, because vertically opposite angles are always equal.
Exactly.
Okay.
So now we have SAS,
Right.
two sides,
Yeah, yeah.
and the included angle.
Mm-hmm.
So we can say that triangle A is congruent to triangle BOLC.
Makes sense.
And because they're congruent,
Yeah.
we know that all their other corresponding parts are also equal.
Right, good old CPCT.
Exactly.
Okay.
And this actually allows us to prove
Oh, right.
that AD is parallel to BC.
Interesting. How does...
That the alternate interior angles,
Okay.
angle OD and angle OBC,
Yeah,
those are equal.
I see. So it's like a chain reaction.
Yeah, it all kind of flows from there.
And does the text have any other examples?
Yes, it does.
Okay.
Example 2 uses SAS in a slightly different way.
Okay, how? So,
It shows a line segment AB
okay.
and another line that cuts through it at a 90-degree angle.
Right. So it's a perpendicular bisector.
Exactly.
Okay.
And it cuts AB right at its midpoint, which we'll call C.
Got it.
So if you take any point on that perpendicular bisector,
Okay.
we'll call it P,
Mm-hmm.
and you connect it to A and B,
Okay.
you can use SAS to prove that triangle PCA
Yeah.
is congruent to triangle PCB.
How so?
Well, AC has the same length as BC because C is the midpoint,
Right.
and the angles at C, those are both 90 degrees.
Because it's a perpendicular bisector.
Exactly. And then PC is shared by both triangles.
Okay.
So we have SAS again,
Right.
two sides, and the included angle.
And what does that tell us?
Well, it tells us that PA is equal in length to PB.
Oh, interesting.
So what this means is that any point on the perpendicular bisector
Yeah.
of a line segment
Mm-hmm.
is the same distance away from both endpoints of the segment.
So it's equidistant.
Exactly.
That's pretty neat.
And this idea comes up all the time in geometry.
I bet.
But it all starts with that SAS rule.
Yeah. It's
It
powerful.
really is.
But the text makes a point of saying that the angle in SAS has to be included.
Yeah, it can't just be any angle.
Right.
And they show what can happen if the angle isn't included. Okay?
What do they call that again?
Sometimes it's called ASS or SSA,
Oh, yeah.
two sides,
Mm-hmm.
and a non-included angle.
Yeah.
And they show that the triangles
Yeah.
aren't necessarily congruent.
Okay, so you can have two triangles with two sides that are the same.
Yeah.
And one angle that's the same.
Right.
But they're not congruent.
Yeah, it's like if you imagine swinging that non-included side around,
Oh, I see.
you can create two different triangles
Yeah.
that both satisfy the condition.
So the order matters.
The order matters.
Like where the angle is positioned in relation to the sides.
Exactly.
Makes a big difference.
All right, so we've covered SAS.
Yeah. Side angles.
What's next?
What other criteria do we have for congruence?
Well, next up is ASA,
ASA.
angle
So,
side angle.
okay, so two angles and a side.
And in the text, this is given as Theorem 7.1.
A theorem.
So it's a statement
Mm-hmm.
that can actually be proven
Okay.
using SAS.
Using SAS, right?
So ASA says that two triangles are congruent
Yeah.
if two angles of one triangle are equal to two corresponding angles of the other triangle,
Okay.
and the side in between,
Yeah.
the included side,
Right.
in both triangles is also equal.
Okay, so again, that word included is important.
It's always important.
The side has to be between the two angles.
It does.
Not just any side. And they actually prove this using SAS, right?
They do.
How does that work?
Well, it's kind of complicated,
Okay.
but basically they look at three different cases.
Oh, okay. What are the cases?
So first they look at the case where the included sides are already equal,
Okay.
and then they look at the case where one side is longer than the other,
Right.
and then the case where one is shorter.
Okay, so they're covering all the bases.
They have to cover all the possibilities.
Right.
And for the cases where the sides aren't equal,
Mm-hmm.
they use some clever logic and construction,
Okay.
and they show that those cases actually lead to contradictions.
Oh, interesting. So they can't be true.
Exactly.
Okay.
And the only possibility left
Yeah.
is that the sides must be equal,
Right.
and therefore the triangles are congruent by SAS.
So they kind of back their way into it.
They do.
That's cool.
It's like building a case,
I like it.
eliminating all the other possibilities
Yeah.
until you're left with the truth.
Okay.
And ASA really does feel intuitive.
It does.
Like, if you think about it,
Yeah.
if you fix two angles of a triangle,
Uh-huh.
and then you fix the length of the side between them,
Yeah.
it feels like you're locking in the entire triangle.
You're kind of defining its shape.
Exactly. There's only one way it can be.
Okay.
So that's ASA.
ASA.
Now we have another rule.
Okay, what's this one?
This was called AS.
AS. So angle.
Right.
Okay, so we have two angles again. But this time, the side isn't between them.
Correct.
Interesting.
Now this one isn't given as a separate axiom or
Uh-huh.
theorem.
Okay.
It actually comes from ASA.
Uh-huh.
And something you probably remember about triangles.
Oh, remind me.
The sum of all the angles in a triangle
Yeah.
is always 180 degrees.
180. That's right.
So if we know two angles in a triangle,
Yeah.
we can always figure out the third one.
Right. Just subtract the 2 from 180.
Exactly.
Okay.
So if two pairs of angles in two triangles are equal,
Mm-hmm.
the third pair must also be equal,
That makes sense.
right? Because if the first two angles are the same,
Yeah.
the third angle has to be the same too.
Yeah, because you're subtracting the same amount from 180.
Exactly. So
Okay.
with AS, if you have two equal angles
Yeah.
and a side that's not included,
Okay.
because that would be ASA,
Right, right.
you essentially still have enough information.
Okay.
because that third angle's got to be equal too.
Yeah, so you're basically using ASA in a roundabout way.
Exactly.
Brother.
So to put it simply,
Yeah.
AS tells us that if two angles and a side of one triangle are equal to two angles and the corresponding side of another triangle,
Yeah.
they're congruent.
They're congruent. Okay.
Now here's something interesting.
Okay.
You might think that if all three angles of one triangle
Yeah.
are equal to all three angles of another,
Mm-hmm.
that they're congruent.
They'd have to be, right?
It seems logical, but it's not true.
Oh, really?
The text uses a figure to show this,
What figure?
figure 7.14.
Okay.
And you can imagine a bunch of different sized triangles.
Yeah.
They all have the same angles,
Mm-hmm.
but they're clearly different sizes.
Right, like they've been scaled up or down.
Exactly.
So the angles being equal only tells us that they have the same shape,
Right.
not necessarily the same size.
Yeah, so they're similar,
They're similar, okay.
but not necessarily congruent.
So to be truly congruent,
Mm-hmm.
at least one pair of corresponding sides also has to be equal.
That's the key.
Okay.
So to illustrate AAs in action,
Yeah.
the text gives us example 3.
All right.
And this one uses figure 7.15,
Okay.
and it shows two parallel lines,
Okay.
AB and CD.
All right.
And there's a point O that's the midpoint of AD.
Okay, got it.
So using what we know about parallel lines.
Like alternate interior angles are equal.
Exactly.
Okay.
And the fact that vertically opposite angles are equal.
Yeah.
And that OA is the same length as OD.
Because O is the midpoint?
Right. We can use A to prove that triangle AOB is congruent to triangle DA.
Wow, so it all comes together.
Yep.
Okay.
And that then means that OB equals OC.
Right, by CPCT.
Yep.
Okay.
So O is also the midpoint of BC.
So it's all connected.
It all ties together.
I like it.
The text then mentions exercise 7.1,
Okay.
which has a bunch of problems.
Yeah.
And these problems involve quadrilaterals
Okay.
with equal sides and bisected angles.
Interesting.
And they really show how these congruence rules
Yeah.
could be used in lots of different situations.
Okay.
So now we're going to shift gears a bit
Okay.
and talk about a specific type of triangle,
Which one?
isosceles triangles.
Oh, isosceles triangles. Okay.
You probably remember these.
Yeah, vaguely.
Two sides that are the same length.
Right.
The text uses figure 7.24 to show one.
Okay.
And one of the really important properties of isosceles triangles
Yeah, what's that?
is that the angles opposite those equal sides
Okay.
are also equal.
Oh, that's right. I remember that.
It's theorem 7.2.
Theorem 7.2. Okay.
It's a classic,
It is.
and the proof is pretty clever.
How does it work?
Well, they use figure 7.25 to show it.
Okay.
Imagine a triangle ABC,
Okay.
where AB equals AC.
So it's isosceles.
Right.
Okay.
Now draw a line from angle A
Yeah.
down to the base BC,
Mm-hmm.
and that line bisects angle A.
Okay. So it cuts it right in half.
Exactly.
And what do they call that line?
Let's call it AD.
AD. Okay.
So now we have two smaller triangles,
Right.
BAD and CAD,
Yeah.
and we can use SAS on them
Okay.
because AB equals AC.
That was given right.
Right.
And angle bad equals angle CAD.
Because AD is the angle bisector,
Right. Okay.
and AD is the side that's shared by both triangles.
Okay. So we have SAS.
So that means those two triangles are congruent,
Yeah.
and that means,
Angle ABD.
yeah, which is angle B
Right.
equals angle ACD.
Which is angle C because
Yeah.
they're corresponding angles.
So in an isosceles triangle,
Yeah.
if two sides are equal,
The angles opposite those sides.
are also equal.
But what about the other way around?
That's a great question.
What if we start with two angles that are equal?
Right.
Does that mean the sides opposite them are equal to?
That's exactly what theorem 7.3 addresses.
Okay.
It's the converse of theorem 7.2.
The converse. Okay.
So the text actually suggests trying this out yourself.
Oh, fun.
Construct a triangle
Yeah.
with two equal angles
Mhm.
and then fold it in half
Okay.
along the line of symmetry.
And what happens?
You'll see this, the sides opposite those angles
Yeah.
overlap perfectly.
So they must be the same length.
Exactly.
Okay.
And this can also be proven more formally
right.
using ASA.
ASA. Okay.
So if you have two equal angles,
Mm-hmm.
the third angle is also related.
Because of the 180-degree rule.
Right.
Yeah.
And then you can use ASA,
Okay.
often by looking at the angle bisector,
Right.
to show that the sides opposite the equal angles
Mm-hmm.
are congruent.
So these properties of isosceles triangles,
Yeah,
they're pretty handy
they are.
for solving problems.
And the text gives us some examples of how to use them.
Okay, let's hear them.
So example 4,
Okay.
it shows a triangle ABC,
Yeah.
where the angle bisector of angle A is perpendicular to the base BC.
Okay, so it cuts the base at a 90-degree angle.
Right.
Okay.
And by using ASA
On what triangles?
on the two triangles that are formed,
Okay.
ABD and ACD,
Right.
we can prove that AB equals AC.
So it's isosceles.
Exactly.
Clever.
And then example 5.
Okay.
This one shows an isosceles triangle, ABC,
All right.
where AB equals AC.
Okay.
And E and F are the midpoints of those sides.
The midpoints. Okay.
Yeah.
And what are we trying to prove?
That the line segment BF
Okay.
has the same length as CE.
And how do we do that?
With SAS.
With SAS. Okay.
On triangles, ABF and H,
Okay.
because AB equals AC.
Given, and angle A is shared by both triangles.
Right.
And AM equals AE.
Because they're half the length of the equal sides.
Right. Okay, I'm following.
The SAS tells us those triangles are congruent.
And therefore, BF equals CE.
Exactly.
All right, what's the next example?
Example 6.
6. Okay.
This one shows another isosceles triangle, ABC,
Mm-hmm.
with AB equal to AC.
Okay.
And this time we have 2 points D and E on the base BC,
Okay.
such that BE equals CD.
So those two segments on the base are equal.
Yeah, all right, and we know that angle B equals angle C.
Okay.